Okay, so why are we here? Okay, so it all started here at the Pufendorf Institute for Advanced Studies. Some of you, or most of you, I hope, recognize this building. It's at the bottom of Sölvegatan. It's a beautiful building that was actually the physics department in the 19th century. Okay, so but, if I had gone to Lund back in the day, I would have worked probably here. Okay, but that's not the case. We still have a very nice building, though, so I'm happy. So what are people doing in this building? So this is an institute for interdisciplinary and transdisciplinary research projects, essentially. So this institute invites research teams that are fundamentally interdisciplinary and transdisciplinary. Okay? So the aim of this place is to be a creative forum, an incubator for new ideas, and a springboard for new research initiatives. And the way it works is that you can apply for a year of sort of funding for your team to be there. You can do it as a theme, that's what it's called. That's a research activity carried out in a large group from at least 3 faculties. And then themes can be subdivided into smaller groups, which we can call threads. Okay? And there are also advanced study groups, which basically is a mini theme. Okay? So it's just a small version of the above. Okay? And this is what we did. Actually, this is what a few people took this initiative. So we had, starting in the autumn of 2017 and finishing off more or less now, was a theme called data, enabling us to better store, observe, and understand what we measure. So this data theme was coordinated by Melvin B. Davis. He's here and there at the same time. Yeah, Monica Lassi. Is Monica here today? Okay, maybe not yet. And Kalle Åström as well. And Kalle is there. Okay. So this is the photo we took, I think, a month before we started, I think, something like this, at the rooftop of the Pufendorf Institute. And we had then 5 threads. First one was archiving vanishing languages. Thread 2, visualizing the universe. 3, discovery from the written word, catalog of stellar spectra. And then the 5th one was understanding how we work together. And these are the sort of thread leaders here. So we have people from the Department of, is it literature and linguistics, I think? Right? Yeah, okay, good, yeah. And that's where Nicole is from. We have Oksana, who's a particle physicist, high energy physics in the physics department. Then we have us here, me and Mattias leading in the visualization team. Then we have Johan Frid and Jonas Björk. And this is a mix then also of the literature, and also the medical science. Philippe Birken from the Center of Mathematical Sciences, and Ross Church from the Astronomy Department, or Lund Observatory. And then we have Catherine Harrison from the Department of Gender Studies, and Monica Lassi, who's a librarian in library sciences. So it's a very mixed, eclectic group of people, right, and from different disciplines, and together we were supposed to solve these sort of problems, right? In the end, it's all about storage, visualization, and then this will be more on machine learning and how to sort of dig out information from texts. Also here, machine learning, understanding how we can get information from stellar spectra in an automated way. And then the final one was then how interdisciplinary work is carried out, essentially. Yeah. So this is quite an interesting group of people. So our thread, again, is visualizing the universe. And we had this statement that we put out sort of, well, in the application, that where we talked about the visualization and mining of large, complex data sets is an important challenge in many scientific disciplines. And we will utilize the expertise of this data team to develop new techniques that will enable researchers to visualize and interact with high-dimensional data. So, and I will come back to what we mean by high-dimensional in a bit. And this work will have applications across a diverse range of research fields, including archaeology, astrophysics, chemistry, and medicine. Because I was involved with this, then we had to add the galaxy astro part of this, obviously. So we had 2 concrete applications that we wanted to visualize, okay, and that would be supercomputer simulations of galaxy formation, which is what I work on, and also leading into new observations of the Milky Way galaxy, which I will mention in a few minutes. So these were the applications that we wanted to somehow, we want to boost how we look at this data, essentially. Okay. And to refine the question a little bit, so can better, more intuitive visualization techniques help us make new discoveries? This is why we do this, right? It's not just to make pretty pictures, but it is to sort of, can we learn more from a better technique, let's say. Okay, so working interdisciplinary, so this is a new thing for me. I don't know, for Mattias, I think in your field it's a bit more common somehow, that people approach you and you want to somehow get your help. For me, it's a new experience, and before this, I was a bit suspicious about the whole process, right? So, interdisciplinary work, before I would think that it's better sometimes for people in natural sciences to sort of solve our own problems, dig deeper ourselves. I'm maybe now and then may take some help from computer scientists, that sort of thing, right, to solve our coding problems and such. So this was a new thing for me. So and I really enjoyed it. And I sometimes in my head I parameterize how much I enjoy things by some number. So my enjoyment Oscar number, and you all have a number. It's just a bit different. And it's somehow related to this, right? So there's some sort of factor of interest, how interesting the project is, multiplied by some level of coolness, then divided by the stress level of your life at the moment, right? And maybe this is a constant, right? But these things can go up and down, okay? Then there are other terms to this equation. You can have sort of distance to coffee measured in meters, multiplied by the likelihood of fika breaks and these things, okay? And in this building, it turns out this is a coffee room, right? So wherever you are, it's sort of close, right? So this is small, this is large, and this number is quite large. So I really enjoyed this, actually. And especially also because the coolness level was high, because, well, as you will see in a second. Yeah. Okay, so then we started off. We had the first day, and here we are, okay? And then our worlds are sort of, our disciplines are really not connected, right? So interaction design, I know very little of this. I think it kind of seems interesting. Astrophysics, perhaps the same thing. I think you find it cool, but how do people work in this field, right? So if you have a Venn diagram of how we work in an everyday life, then it's sort of like this, okay? Then you have a coffee, okay? You start off your day, and then you first take care of the important stuff, sort of the things we sort of care about in our on the side, right? So all of the 80s pop culture stuff, Easterband, old computers, Jugendstil architecture, and these things. Okay. Then you find somehow like a way to interact, right? Suddenly, then we talk about the work, what we do. We understand each other a bit better, right? So suddenly we don't change these circles, but we somehow we find a connection point. This is sort of what I found, right? It took a while, but I think when we found how to do this, and then we can somehow start drawing things on the board and experiment, right? But I think so we had to take this route to find the sort of the entry point of the collaboration, I think. And it's not only me and Mattias, right? So we have many other people who was a part of this. And I need to mention especially Henrik Garde and Simon Holk. So Henrik is at the Hum Lab. Simon is a student at LTH, okay, working with also Mattias. And so these have been crucial for the work I'm going to show you in a second. Then we also have Diederik Niehorster, who is working at Hum Lab. I don't know if Diederik is here yet, but yeah. He will talk about eye tracking and probably virtual reality in the afternoon as well. Okay. So these people have been involved in creating these doodles on the boards, right? And you will see what came out of this in a few minutes. And then, of course, the second we started doing this, we sent out a press release as a part of the Pufendorf machinery, and the hype became overwhelming. Okay, so we had done nothing at the time, and suddenly everybody was talking about what we were about to do, right? And so the stress level increased a little bit. So enjoyment went down a little bit, but it was fine. Okay, but yeah, it was all fun and games, right? So we had to deliver, of course, after this. Right? Again, I will show you what we came up with in a short bit. Okay, so now we can come back to this question now. Can better, more intuitive visualization techniques help us make new discoveries? Okay. So let's take a little step back and consult Wikipedia. Scientific visualization, what is this, right? So probably not always the best source for information, but let's see what they are saying, right? So it's an interdisciplinary branch of science, okay? Primary concern, according to some people, with visualization of 3D data, phenomena, emphasis on realistic renderings of volume, surfaces, and so forth. And I think the last sentence here is a bit interesting. The purpose of scientific visualization is to graphically illustrate scientific data to enable scientists to understand, illustrate, and glean insight from the data. I think it's the gleaning of insight that we want to get to in a bit here. Okay, so can we learn more from this? Because most of the time when I hear about this, I tend to think about these things. Right? So sort of pretty front cover pictures of fancy magazines, right? So where you have some visualization of some data, right? But do we learn more from this or not, right? It's inspirational, maybe, right? But can we sort of get more out of it than just a nice color map or something like this, right? So it's a part of science, I think, to do these things, to visualize in terms of outreach of these things. But in everyday research, do we learn something from this? That's the sort of critical question, right? And I should say that at visualizing data in 3D and such, it's not a new thing, right? So this is a nice example from 1874. It's one of the most notorious physicists in the world, James Maxwell, who's most famous for formulating classical theory of electromagnetic radiation. He also was very much involved in developing thermodynamics at the time. And people here who enjoy thermodynamics, and I'm sure we all do, then it's a lot about differentials, right? And equations of differentials, right? So if you write some change in the energy, then you can expand this, right? In terms of differentials like this, right? So derivative of the energy with respect to the entropy, and then you have all these variables, right? And he wanted to understand, so what are these equations telling me, right? So he picked an element, in this case some water-like substance, and he basically used, it's basically this equation that you see here, right? So you can create some sort of surface, isocontour surface, okay, where you have on the x and y and z axis energy, volume, and entropy. So this is the plaster, the cast that he devised at this time, okay, and this is a diagram. So he also thought that you need somehow to feel your data somehow, right? You need to get a feeling for this, right? So he didn't have access to matplotlib at the time, obviously. So this is what he can do. And it turns out, when I looked at this a bit more deeply, it turns out this was not an uncommon thing for people to do at the time, right? When you have multidimensional data, you would create a model of this one. Of course, when we come to galactic science, things get more complicated, okay? So this now is the most modern view we have of the Milky Way. This is the positions on the sky of stars taken by the Gaia satellite, which is something that the Lund group is very much invested in. So this is, the points here is basically more than 1 billion sources, right? So we have positions of stars, velocities, brightnesses, and these kind of things for a lot of sources, right? So it's a very rich data set. And now, making use of this is complicated. It's a very big data science, okay? But there's a lot of hidden features in this data that we would like to dig out, okay? So how do we do this? And an example of those kind of things will be streams of stars, okay? So we know that during galaxy formation, this is now the Milky Way galaxy, an artist rendition, we have lots of little satellite galaxies, small galaxies called dwarf galaxies. They fall in, they deposit their stars, often in streams, and they wrap around the galaxy. So knowing where these are, and how many of them there are, and the mass of these things, and the other parameters of these streams, will teach us how the galaxy formed in the first place. So it's a hunt going on to quantify these streams of stars, right? And here's some older observations where you can see a lot of these things, right? So on the night sky, you have these sort of streaks, okay? And so it's like a junkyard of galaxy formation. And again, by identifying these things and digging into the data, and we will learn how the galaxy formed, right? And so this is one application where we think not only traditional analysis is very useful, but also better ways of interacting with large data sets. Okay? And again, I will come back to this even more at the end of the talk. Okay? Okay, and the work I do is computer simulations of galaxy formation, and this is basically the idea behind this. Okay, so you have, so what I do is then very much numerical computational science. So we have the laws of physics here, okay, and we discretize these and we write them into some, we create some kind of code to evolve some system using, governed by these equations. We have initial conditions of the universe. It turns out to be one of the earliest observations of the universe, the cosmic microwave background radiation field. Then we put these into a computer, we evolve this, and then we hope we get a galaxy out. And by varying these equations, we can then learn how the physics of galaxy formation occurs. Okay? So we are playing a creator, basically, right? By modifying these things, we learn about the physics of this process. And this is what it looks like. And this is now showing you a large patch of the universe. We have the gas from which the stars will form. Okay, each little lump here is a galaxy. Okay, so this movie will evolve for billions of years, actually close to 14 billion years. And at the end of the simulation, we will see a disk galaxy like the Milky Way to form, right, somewhere around here. Okay. And you see it's a very violent phenomenon, right? And this is just a very small part of the data I'm showing you. So we have all these spatial dimensions and time. We also have other species. We have the gas, the stars, the dark matter. They all have their own metadata, which we can show and analyze, right? And it is again very complex. Okay, and we can do a lot of work on this. I can sort of ask, what is the mass of this galaxy? What's the size of this galaxy, right? So these things I know I'm looking for. But the problem is to find the things I don't know I'm looking for, right? And so to do this, I think one needs to sort of play with the data, and I think here is where scientific visualization plays a very big role, according to me. Just give you an example of the discoveries we can make from this data, just visually, which will then lead to something more quantitative. So this is what this simulation more or less looks like on large scales. This dot here in the middle, this is actually the dark matter, the matter I did not show you. So this is an undiscovered, probably an undiscovered heavy particle that particle physicists are looking for as we speak. But if you do a simulation, you can make an approximation of what it is, right? And this is what happens then. So we have all these lumps here where galaxies ought to form, and this is where we think a Milky Way-like galaxy ought to form here in the middle. Right? So if we then switch to view just the gas of this system from which the stars will form, it looks a bit different. It's quite filamentary, and not all of those halos or lumps of dark matter contain galaxy-forming material. Okay? So that's one insight just from looking at the data. Then we can have a close look at this region of space, okay? And we can separate the metadata we have into different colors. Okay, so we can have the gas density here. We can put the temperature of the gas here. Okay, so hot gas is more, it's more intense, and cold gas is dark. Right. Then the heavy elements, so things heavier than helium, things that form inside of stars and is ejected into the medium outside. And then we can combine this, okay, into some RGB image. So we did this now almost 10 years ago, right? And we were just playing with this to get a feeling for what happens. And then we found this new mode of galaxy formation in this while doing this. So we found that galaxies form in multiple ways, okay, so at the same time. So we basically here have disk galaxy forming. We see here these blue streaks here, so we call cold gas accretion or cold flows. So this gas is flowing in from huge distances, okay, and assembles the galaxy very rapidly. At the same time, we have this in red, this shock-heated gas, so hot gas that smoothly falls onto the galaxy. Okay? So we have a bimodal sort of way of forming galaxies at this in the early universe. Okay? And this is, and other groups found this as well. Okay? And it really took off just because people just looked at the data, right, and played around with it, and they found this way. And because people didn't know what to look for otherwise, right? So people were guided by just images, basically. Now, a few other examples, and now I will expose my colleague here, Florent Renaud. So how do we do things? Okay, so those are just pictures that we look at, right? So when we publish papers, what does it look like then? This is very different in different disciplines, okay? And in our case, in astrophysics and computational astrophysics, what do we do then? Do we put all these images into papers and then hope the reader will discover something? So it's not really this way, right? So I'm showing you this paper because I think Florent is making very nice visualizations of his data. Also because I'm on the paper, so I can sort of self-promote myself while promoting Florent. Okay, so it's great. So this is a paper published 2016. Okay, actually it was published 2017, yeah, last year. What happens is that quite often when we do these models, there will be a figure in the paper showing you this is what it looks like so some pretty picture that builds intuition for the reader. Okay, so this is sort of like the simulation I showed you before. You make some snapshots, you show this, and it can be discussion qualitatively what happens, right? So I think this is now the honest thing. Most simulators want to see this, right? Show us your simulation, sort of what it looks like. You can get a feeling for the resolution if you start looking at this, right? Then, okay, we go into more quantitative analysis, right? So now, as I showed you here, right? So all of these little lumps here, they merge together to form a galaxy. And you can quantify this using something like a merger tree, okay? So this is now how the galaxy, this is basically time here. And all these lines are how the different little small galaxies connect, right, to the big galaxy. Okay? And then of course, all these small galaxies also have their own branches, right? So they also form in a hierarchical way. Okay? So this is now somewhere in between a very hardcore quantitative analysis and a visualization of the data, right? So we get a feeling now for this is fairly a large thing maybe, this is a bit of a more complex thing falling in, right? And we can somehow look at this to get an intuition for how this complex simulation is progressing, right? I think it's a very nice way of doing this. And then, and then usually the rest of these kind of papers will be filled with traditional analysis visualization things, just plots, right? So some variable versus another, right? And so, star formation rate of the galaxy versus time or something like this. Okay? So I think it's this mixture that I think builds up a nice paper when you do the things I do or we do. Yeah. Okay. So moving on about something about the scientific process then before we go over to Mattias' part here. So to me it's about this then making discoveries in data. Okay, and the textbook approach of the scientific process is something like this, right? You have a question, you have a hypothesis, and then you make a prediction. Then you run an experiment. Okay. Then you analyze the experiment, and then you have a conclusion, and you write a paper, and you're happy. Okay? So this is sort of the sometimes what the science councils wants to see, right? When you apply for money, okay. But I think this has to be augmented or maybe nuanced a bit, right? It's not completely what happens, as I think we all know. So in reality, we get something more like this, right? We start with ignorance, we don't know anything. Then there's some intuition or observation or a conversation you have, and you get an idea, right? Then you have a question formulated, and you know it's the best question in the world, right? Then you do an experiment or calculation, and you have failure. You have some more inspiration, creativity. You come up with a new idea. You revise your experiment. You fix it. It fails again. You get slightly depressed. Then there's a moment of inspiration again, creativity. You revise this. And at some point down the road, you have a better question, right? So it's not only that you have a conclusion, you just refine your question into something better, and you hope at some point you actually have a conclusion. That means you solve your field, basically, right? So it's all about, I think, this, right? They're getting to better questions, and it's the point number 2 and 6 and 10 here where I think visualization plays a very big role, right? To inspire you, right? And then you reformulate your theory from this. And towards better questions, I think this is actually now, I didn't think I would do this, but this may be a cite from Donald Rumsfeld in 2002, actually, so bear with me. So it's about the things we know, okay? So if you make a matrix like this, what we comprehend is on the y-axis, what there is to know on the x-axis, then we can make this matrix of unknowns and knowns, right? And so we start here. These are things that we know, okay? Then we can start filling in all the other blanks here, okay? And the most interesting one, the traditional one that we approach is this one, right? What we know we don't know, okay? So in my case, it's like I want to measure the masses of all the galaxies in my simulation. I know they have masses, so let's measure them, and then I publish this, okay? But it's this, again, we're coming back to visualization, is what we don't know, the things we don't even know what the question is, right? That's where I think we need the creative, inspirational process, right? And that's, I think, where we both see these kind of strange technologies and visualization techniques to be very useful to get here, right? This is, and once we formulate the question, right, then we drop down here, of course, and we start the machinery in some sense. Okay. So before I leave the clicker to Mattias, so in many ways, when I work on my simulations, I may produce something like this, okay? So this is a simulation output. Actually, it takes months to do this, or even half a year. Okay, and in the end, I may look at this and say, look, this little galaxy here, I want to look at this a bit more, in more detail. So I always wish that my way of visualizing was a bit more like this, like playing with Lego, right? I would twist it around and I would change pieces, and I could interact with the data in this way. Okay, So this is, I should say this is me playing with Lego with my 3-year-old son, but it's just me playing alone with Lego. So. Okay, so now I'll hand over to you, Mattias, but we're going to say that we want to revise this question as well then. I think, can we improve the way we interact with data in addition to just visualizing the data? I think this is where VR has may have a positive impact, okay? So,
you see. All right, you hear me? If I talk like this, excellent. So just very short presentation on myself for you who have never seen me before. This is me. All of this is true. Probably this is the most true one. My mother is still wondering when I will get a real job. Anyway, so I usually spend my time here at the Design Center, which Oscar already mentioned. And this is the kind of research I usually do. It's a mixture of interaction design, human factors, virtual reality, augmented reality. So that's what I find most interesting, and all the research I do have something of these 3 elements here. So first, before we dive into this, what is actually VR? Most of you probably have an idea, but let's dig a little bit in the history of VR. And actually, we have to go back to 1968, 50 years ago, isn't it? Or 40? I'm a bit tired in the head. 50, right? 68, yes. Yeah, that's 50 actually. Yeah, sorry. When the researcher Ivan Sutherland, who is usually referred to as the grandfather of computer graphics, he actually invented what is considered the first virtual reality system, or maybe even augmented reality system. Maybe not so impressive for us, but to think he did this half a century ago is quite cool actually.
What was the name of this? It was the Sword of...
Yeah, the Sword of Damocles. Actually, it's because this thing that it's a mechanical tracking system. So here you have a really heavy thing, and it's connected to the Greek myth of Sword of Damocles, so that some of you might have heard of. Like being a king is like sitting on a throne with a sword over your head. And that's how people felt when they used this thing, that they felt it could fall down any second and just spear them. So that's why it's called Sword of Damocles. Fun facts. Okay, let's jump to the 90s. And yeah, some of you were around back in the good old days. And this is what happened then. That was a huge, huge, huge hype around this new technology. A number of companies came from nowhere, basically, like VPL, and promoted this technology as something new and fantastic that really could immerse you in new types of worlds. But as you all know, technology wasn't mature yet. So after a couple of years, the interest started to go down, and it was considered a failed industry, more or less. And it kind of survived as a big, expensive technology, mainly at companies and universities, like in our VR lab here at the university. Big, expensive systems, very difficult to maintain and develop and so on. But a couple of years ago, suddenly we start to see systems like this. You can really immerse a user and make them feel like they're actually interacting with a robotic dog, which is something everybody wants to do, of course. So this is actually what it feels like to use a modern virtual reality system. And we have a couple of them rigged outside that you will get to try later with coffee if you want. So that's virtual reality. But why virtual reality? Why should we care about this? I mean, it's not... I mean, we can throw sticks to the robotic dogs is one thing, but how can we actually use it? Is it just because we can? We have all these companies in USA, in China, all over the world that produce really cool hardware, and the prices are sinking very, very quickly. Or is it because we should? And this is, as you probably know, how computers traditionally perceive humans. It's like a big eye, some ears, and like fingers, or yeah, one finger to poke the screen. But we are so much more than this, right? For example, just take multimodal perception, which is a very, very important part of how we as humans operate. So, yeah. For example, with a hard time saying that word, ventricular. Thank you. Thank you, Shamit. The phenomena that makes us believe that the sound is actually coming from the mouth of the doll, where it's actually the girl to the right the sound comes from, but our brains tricks us to perceive the sound as coming from the doll. And this, some of you might have heard of the rubber hand illusion, where you can actually trick your body to think that the rubber hand is part of your own body, and if somebody threatens it or, like here, slamming it, you will react as if it was your own hand. So the brain is very, very plastic in that sense, you could say. Another phenomena that is discussed very much these days is embodied cognition, and this is the idea that we just don't think with our brains, but also our whole organism. The body is very much involved in this. And as this article here states, much of the work required to achieve our goals, replacing the need for complex internal mental representations. And that's exactly where VR comes in and can help us, bringing the body into the equation, so to speak. And as an example of this, Oscar had a really good example with Maxwell and his plaster models. This is another example of famous researchers Watson and Crick, who found the structure of the DNA molecule, the double helix structure, pretty much by playing around with the cardboard models in this way. Of course, combined with a lot of simulations and mathematical work, but this is how they finally understood that this is the way this must be shaped to make all the distances between the atoms correct and so on. So very much embodied work in this case. But okay, fine. Humans are much more than just a big brain. We have this new cool technology, but isn't this actually just another VR hype? We had one in the 90s. Why is this different?
Do you need sound, by the way? Or? Do you need sound for this?
If there is, would be great.
I think I turned it off. Okay, let's see if we can hear something. Yeah.
Okay, so how do I actually start this?
You click here.
Where is the clicker?
Click on the right, yeah, just forward.
Okay. Do we have some?
Journalister, affärsfolk och så vidare, de kommer vi att möta också i programmet. Sen finns det då ett avsnitt om hemdatorer som jag personligen är något lite mer skeptisk emot. Det talas i programmet om att vi allihopa kommer att sitta hemma då och beställa biobiljetter och sådana saker. Jag tvivlar på det. Själv har jag haft dator hemma i snart 4 år och jag hittar ingen som helst privat användning av den. Det är faktiskt så att telefonnummer hittar man enklast i telefonkataloger. Kakrecept hittar man enklast i bakböcker och matrecept lämpligen i kokböcker. Boken är ett sällsynt bra sätt att förvara stora mängder information i. Det är också så att de här så kallade hemdatorerna, vad man nu egentligen menar med dem. Men om man menar det som det är vanligast med sådana här hemdatorer, nämligen att man kör dem på sin egen hemma-tv, så har jag ett bra förslag till alla som funderar på att skaffa sig någonting sånt. Sätter 3 kvällar i rad på 40 centimeters avstånd från er färg-tv hemma och så tittar ni igenom Rapport kväll efter kväll 3 kvällar i rad. Om ni fortfarande vill ha en hemdator så köp för all del en, men jag tror inte att ni kommer att ha någon vidare användning av den. Annat än i ett avseende, och det är om ni vill lära er programmera så går det alldeles utmärkt att göra det också på en liten hemdator. Men att göra något meningsfullt hemma med den i övrigt, möjligen då spela spel, det kan jag inte se.
Okay. So this is one of back then Sweden's most respected journalists who sits in Swedish television prime time and says things like this. It kind of gives us a perspective of how people were thinking back in the 80s, where computers started to enter our lives. And sometimes we who work a lot with VR, we get a little bit the same feeling, because people usually say like, yeah, I mean, come on, games, sure, but what else can you actually do with VR? Come on. So I think we should learn a little bit from history. And you can also look not so long ago, like 2011, Bert Nordberg, former CEO of Sony Ericsson, said this. And I happened to have a PhD student who worked at Sony Ericsson during these days, and I had got some interesting inside stories, how they were reasoning around the threat from Apple. And it's kind of sad when you think about it. So basically, to summarize, what is happening right now is we are, whether we want it or not, we are actually moving from desktop computing to more immersive computing. So 1981, you could play around with your Xerox Star computer system, with the Star interface, which was the first operative system to use a desktop metaphor for the user interaction. But today, you can actually walk around inside Windows 10 with your Windows Mixed Reality headset and do the things you would normally sit and do in front of a desktop computer. And I think that actually says something about where we're heading. Yeah.
Okay, so let me just do the last couple of minutes here. Okay, so then what we're getting to then is, will virtual reality enable us to do more, well, to more intuitively inspect complex data sets, right? And as Mattias was alluding to. So, and then also, do we want to play with data in this way, right? That's something we'll get to. So let me just show you what we've been up to. Okay, so this is me here. So this is what a thing that was developed by, let's say, me and Mattias, but mostly I would say also by Henrik Gade, who I mentioned before, and the person who put this all together in the end and helped out with the filming is Simon Holk. Okay, so I think he's in the audience, and everybody should give him a job or two because he's really, really good. Okay, so this is now what I'm doing here. Okay, so now this is me interacting with data from one of my simulations. Okay, we chose simulation data because I know what it is, and it's easier to export this. Okay, but any data set will work here. So it's a galaxy. It's hard to see on the screen now, but it's color coded by the age of the stars in this case. And the little lumps you see here are called star clusters. Okay, so these are where we think most stars are born. Okay, in these dense configurations, and then are spread out across the galaxy. Right? And this now is a tool that's developed in the Unity framework, and this is a framework mostly dedicated to gaming. But as we can see here, it's not too complicated to get data loaded in, any kind of data, right? And the good thing about Unity is that it's highly compatible with all of the modern technologies, right? So if you get it in here, you can press play and run it on your screen or your VR headset, right? So what I showed you here is that I made a cutout of the galaxy. So I thought this little piece is interesting to me. So I can walk around with this in front of my face, basically, okay, and look at it from different angles. I have a little control panel here in front of me where I can do some analysis. So I'm demonstrating a simple analysis thing here where I plot a histogram of the ages of the stars, right? And because I now have the workspaces now of the room, right? I can put these across the room if I want to, right? And walk around. It's great for looking from different angles of this data, right? So I can go up to a star cluster and see if it's slightly bluer or redder in some parts of it, right? And that may tell me about how it formed, right? So here I chose some of the younger stars, and they are a bit more clustered. Okay, so I'm pointing out these little systems here. Okay, and if I instead select from this histogram, okay, here's a bit more of the younger stars. Okay, and now I can sort of inspect this in a super intuitive way. It's quite impressive once you try this out, to be honest. I can select the old stars in this demo. Okay, and they are as we expect. Actually, they are a bit more spread out. Older stars somehow they phase mix into the galaxy. And I get something much more smooth, right? And what I can do here, I can actually now, in principle, I can bring up hundreds of these little patches of the galaxy, compare them, right, in front of my face, right, and add them to my room, walk around, and just interact with the data in this way. But this is now, essentially, this tool here is, let's see, in terms of development time. Okay, so Henrik may spend some time just getting the loading of the data in, having a pipeline for this. And then I guess Simon, I don't know how many weeks you spent on this. Is Simon here, by the way, or is he over there?
I think he's actually outside.
He's waiting there, okay, yeah. So Simon, he probably spent like, a few weeks getting things up and running, right? And then you can refine on how you do your, how you do all of the interaction, and you can add more features to this, right? So it's essentially, at this point in time, it's like it's a fancy GNU plot, essentially, right? So you load your data, you can do things, and it's sort of all we would like to have as a first step, right? And you will get to try this out there in the corridor later. The other thing I want to highlight, which you will try, is a much more advanced thing, much more developed thing, which is called Selexel VR. It's developed by Schmidt and his team here. So I was thinking I want to sort of show this a little bit, but to give it justice, maybe do you want to say like a few sentences of what this is, right? I can make something up, but yeah. But this, yeah. So I'll give you the mic here, right? So So I think this is the best example of virtual reality applications in Lund at the moment, to be honest. So.
Yeah.
Is it on or? It's on. No. Yeah, it is. It is on. So yeah, so it's he will get the sound, but. Yeah.
Okay, cool. Can you hear me? So the idea was that we have a lot of single cell expression data, and a lot of this data is actually in 3D, the way that we look at it on the screen. But it also made it very frustrating to work with, because when you rotate these 3D plots on the screen, they're not interactive, but they still look flat. So you have no perception of depth when you're working with it. And also we have many representations of the data as well. So and they obviously appear in different windows, so they can't talk to each other. So the idea was that with VR you can have everything, all of your data objects in the same environment, and everything should be able to talk to each other in a very intuitive way. So that's what we set about doing just over a year ago. So we got in contact with Mattias at the design center, and he hooked me up with some very talented students who have been working on this. So, I mean, in time-wise, we're probably talking, one person and a bit full-time for the past year got us to this stage where we are now. But yeah, we have a demo running outside, and I'll be on the panel later as well, so we can talk about this more.
Great. Yeah, thanks a lot. Yeah, so it's as Shamit was saying. Yeah, it's really a much more developed tool than we have. But yeah, I think we both are facing similar issues that we will bring up later, which is the big data, right? Getting lots of data in and crunching this while we interact with it. So, okay. So a few things I want to mention because of this. It's a moment of virtual reality. So something that we have done in the past year is also to start a course on computational. Virtual reality in computational research. So we ran this in the spring, and so I coordinated this, and we had a bunch of lectures from different faculties, right? And so it's a very interdisciplinary course to take on, and we had a few students who did it really well. I think we have where they got the data to load it into Unity, and they can interact with it. So it was a fun experiment to do, I think, and it really taught us a lot on how the natural sciences may adopt this technology if it does. Right? Then there is another effort going on now. We have some funding from Essence, so the eScience collaboration here in Sweden, which is the PI by Stefan Lindgren, who's here in HumLab, the motion capture lab, with a bunch of co-Is, names you now may recognize, where we over 3 years we will spend some time developing a framework for any data, essentially. Okay, so an API for big data or small data to be loaded into a VR framework where it can either be visualized in VR or also augmented reality, big screens, tablets, etc. So a general somehow pipeline for data to be visualized in multiple ways. That's the idea with this. Okay, and so we're soon going to go out to the corridor here. I hope the coffee has arrived. I'm not. Yes. Yes. Okay. Good.
I think.
Okay. So. Okay. Yeah.
I hope.
Yeah, yes. We will have some hands-on demos, as we were saying before. This is what we have on show out there. We have two these are the technologies or the gear we have. So HTC Vive, two of these most common headsets. We have two of the standard one, a new one of the Pro. Okay, so this is a much more high-res display. We have this out there. Samsung Odyssey is another setup which doesn't require the trackers, right? The lighthouses. You can do this just with with this system. And do you need a web camera as well, or do you need? No, it's just these systems. Yeah. Augmented reality. We have a HoloLens you can try out there, and we have this guy here, the Oculus Go. I think this was released seconds ago, essentially, right? It's new, right?
Yeah, it's still warm.
Yeah, and I should say that these technologies. I mean, it's not really like we're showing. The best there is in the world, right? These are commercial things you can buy in Elgiganten, right? In the store. Okay, so I think this is $200 or 200 euros or something, right? So it's a lot of these for one iPhone, for example, right? So it's meant to be cheap, and we want to see can we harness this sort of the low entry point, right, and use it for science. That's the idea, right? And if this was very expensive, we may not go there. I think in the same way. Now these are very affordable systems. Yeah. Okay, so let's, and I think when you try these things, please keep a few questions in mind, because we're going to have a panel discussion, and we would like to have a critical look at these things, right? So now we're all very happy we're doing this, but there's a lot of issues. So first of all, what are the possibilities that you envision with VR? What are the risks? How would you like to use VR? So if you want to sort of bring something up later, please do, raise your hand, and we'll talk about this, okay? We'll add more things to this list as well, right? But I think these are good things to keep in mind while you try things. Okay, so let's end here with a quote from a famous scientist from a few weeks ago. Okay, and the coffee ought to be coffee ought to be served. Okay, and the setups, how to describe it? It's down the corridor to the left. Okay, and yeah, so please bring your coffee over there, try things, and mingle. And we have an hour and a half, and then we'll break for lunch. Okay, and then we'll see you back here at 12:30. Okay?
Excellent.
Yep.